Earlier, our text-to-image generation started from a blank canvas. However, in many cases, we already have an existing image and only want to modify it. This is where image-to-image generation comes into play. Let's first revisit the basic text-to-image workflow. As seen in the previous demonstrations, the sampling phase critically depends on three inputs: model, prompt, and latent space image. During text-to-image generation, the latent space input is an empty noise image, initialized according to desired dimensions. For image-to-image generation, you simply replace this noise image with the image you want to modify in latent space format. Let's try it. Add an image loading node, then connect it to a VAE encode node to encode the original image into latent space format, replacing the previous empty latent image. The purpose of image-to-image generation is usually to modify, not redraw, the whole image. I'll specify anime style in the prompt. The critical parameter to adjust here is the denoise value, which is arguably the most important parameter in image-to-image generation. It determines the proportion of the image that the model rewrites relative to the original image. The range is from 0 to 1. A value of 0 means the original image is completely preserved. It will look like nothing happened. A value of 1 means complete reconstruction, equivalent to text-to-image generation. Our goal is style transfer, preserving the original composition but switching to anime style. Set denoise to 0.75 and click Run. You'll see that the generated image almost perfectly maintains the composition of the original, but the details and brushstrokes have clearly transitioned from realism to anime style. If we experiment with different denoise values, we get a set of comparative results. Let's take a look at the actual evolution process of the image in image-to-image generation. Replace the standard sampler node with a process visualization sampler named KSampler Progress. It's part of the third-party plugin Inspire Pack. Connect all previous inputs, set output to process latent to export all images during the process, and keep other parameters the same as before. Set noise mode to CPU for exact reproducibility. Click Run. Unlike text-to-image, the first frame is still high noise, but you can already discern the outline of the original image. With each iteration, the noise is gradually erased, anime style lines and color blocks become clearer, and finally, the style transfer is complete in the last frame. In many cases, we don't want to redraw the entire image, but only modify a small region. That's where masking for inpainting comes in. Go back to the basic image-to-image workflow. This time, no style change, just alter the character's tie color from red to yellow. Add a dedicated VAE encode node for inpainting, replacing the previous standard encoding node. It accepts an additional mask input. Next, generate the mask. Right-click on the image and choose Open in Mask Editor. In the pop-up interface, your mouse becomes the brush. Carefully paint over the character's tie. You can adjust brush color and size, as well as mask transparency, using the tools on the right. When you're done, click Save. Back in the workflow, you'll see the masked tie area covered in black. The encode node offers a mask dilation parameter, which expands the mask edge slightly to avoid harsh seam lines. Keep the default 6 pixels. The prompt should focus on the content within the mask. Just enter yellow tie. Click Run. The result is ideal. The tie color is successfully changed to yellow, while the rest of the image remains unchanged. If you want to reuse this painted mask in the future, use the Convert Mask to Image node to export and save the mask separately. When using it again, upload both the original image and the saved mask, then use Convert Image to Mask node to switch the mask image into mask format, allowing quick local edits without repainting. There are some limitations to local edits via image generation models. For example, style consistency across the mask border isn't perfect. Edges may become blurred or discolored. Complex structures such as hands, faces, text, intricate patterns may easily break. To address these issues, advanced pure inpainting models have emerged, capable of generating highly coherent new content based on the context of the existing image. For example, the Fill series models in Flux tools. Let's use it for inpainting. Load workflow. Select the Fill model from the Models Diffusion Models directory in the Model Loading node. Different quantization versions are available. Here we'll use FP8. As a member of the Flux family, it also requires Clip L and T5XXL for Clip, and Flux VA for VAE. Mask the tie area as before, enter the prompt, yellow tie, and click Run. The result is flawless, natural color replacement, clean edges, and no mask-induced style break. While this simple case doesn't showcase a dramatic difference, In the following local editing scenarios, the fill model's superiority will be much more apparent. It can also be used for outpainting, expanding the image beyond its borders. Create a pad image for outpainting node, expand 200 pixels to the left and right, then pass the extended image and corresponding masks which mark the newly added regions to the downstream nodes, providing prompt and latent space image for sampling. Prompts for outpainting can be left blank, letting the model freely extend based on the original image's style and semantics. Once generation is complete, the expanded areas on the sides blend naturally with the original image, and the style is well integrated. All the editing methods just described are manual. You need to use masking tools on the image, provide prompts for content regeneration by the model, and finally merge back into the original image for the editing effect. But the new generation of image editing models is far more convenient. You simply provide instructions as prompts. The model comprehends and modifies the image directly. Among open-source image editing models, the most popular are Flux Kontext and Qwen-Image-Edit. Load the context workflow in ComfyUI. Its model also goes into the model's diffusion models directory. Clip and VAE requirements are the same as the Flux family. Kontext supports low-RA, but for now, we'll disable the low-RA loading node. Enter your instruction in the prompt, change red tie to yellow. No need to modify any other settings, just run. The automated result is no less effective than the previous manual approach. Next, try the domestic Qwen-Image-Edit model. Load the corresponding workflow. Qwen models use clip and VAE with the Qwen prefix, differing from the Flux series, though the file placement path is the same after downloading. It supports Chinese instructions as prompts, but also works with English. Let's keep the instruction consistent with context. Click Run. The editing result is also very satisfying. Of course, instruction-based editing models have limitations. They only work optimally at specific image sizes or resolutions, lack the precise control of masking, and sometimes cause modifications to spill into other regions. However, they excel in convenience and also has ecosystem support such as low-RA, ControlNet, etc., and are highly likely to become the main direction for image editing in the future.